My name is Eric Atby. I'm an enthusiast for all things nautical and aerospace. I served for 22 years in the U.S. Submarine Force and have been supporting it for the last 14 years since retiring. I've been an aviation enthusiast since I was 10. Please join me while I pursue my passions through first-person experiences in history, exploring aircraft, ships, and historic sites that have changed the world, and for some that are truly off the beaten path.
Welcome to Seattle, Washington, to Boeing Field, home of the Museum of Flight and home to the very first 737 ever produced. Tail number November 73700 first flew in April of 1967, with the type entering service in early 1968. After completion of flight testing, it was sold to the National Aeronautics and Space Administration, or NASA, where it was given a new tail number of November 515 November Alpha, where it served as a test bed for new technologies. A total of 30 of the Dash 100s were produced before Boeing started an iterative improvement cycle on the 737 that still continues to this day. As of the recording of this video, 57 years after the first flight, this is the only surviving Dash 100 model. Now, let's take a look at what made this aircraft so successful. The 737 had several attributes that made it such a commercially successful and hugely popular airplane. These are, first, it had a common cockpit carried forward from the 707 and 727, but with improvements that removed the need for the flight engineer and only required two persons to operate. Second, it was introduced with two turbofan engines mounted on the wings. Having just two reduced operating and maintenance costs. Third, it had high-performance lift devices on the wings carried forward and improved upon from the 727. Fourth, it moved the auxiliary power unit, or APU, to the tail of the aircraft. Fifth, it had the same six abreast seating and cabin dimensions as the 707 and 727. And sixth, it had a lower seating capacity than a 727 and 707 and were able to operate on short and medium thin routes that were not economical with prior aircraft. As we take a walk around the front of the aircraft, one thing that you notice is that the nose of the aircraft looks almost exactly like, or is exactly like that of the 707 and 727. That was one of the things that was carried forward. The early models of aircraft, the dark black that you see there on the nose is actually so that it can have radar fitted. It was a different material. And you can see there one of the add-on sensors, I believe that was an infrared sensor that they had for whenever they were doing flight testing with new sensors. And we'll take a look down here at the nose gear. Does not have any braking capability, rotates directly up, and it's basically right underneath the floorboard of the cockpit. See that it has several different pitot tubes and angle of attack sensors. And standard cargo entry there for the forward hold. And you can also see the heat exchanger duct inlet that you see there for exchanging heat out of the air-conditioned air before it gets filtered, or not filtered, provided into the air mixer. And you take a look here at the wing of the aircraft, the Kruger flaps on the inboard portion, the engine. Then on the outboard portion of the wing, it has the slats. The Dash 100s and very early Dash 200s had an interesting setup that the outboard, the furthermost outboard of the slats, had two positions, but the inboard slats only had a single position. I'll show that in a picture here, so you can just see that. That was just an interesting thing that in the advanced 200s, they corrected that and gave the innermost slats the second or landing position as well. And making our way along here along the wing. It's a very clean design, eliminating as many small perturbations and making it as smooth as possible. Now we'll walk back in here and take a look at a couple of the pylons that are used to house the flap extension mechanisms. You'll see here in a second whenever they extend out that these are triple slotted Fowler flaps that you'll see. And then at the very edge of the engine there, we'll take a look here as the flaps come up here, just to show you how they articulate up. And you'll see there at the edge of the engine, those are called the flipper flaps that come down in that little track. Since the engine is wider than the actual control surfaces, it stops those sections and allows the rest of the flaps to continue on. 737, that interesting bit about the main gear, they fold up into the fuselage there, but there's no door that covers over the tire itself. You'll see here as it comes out. So you see that there's a fairing over what would be the outside wheel that allows it to be faired in. But if you ever see a 737 in the air, you can see the tires. And the aft baggage hold and aft entry door. And that silver thing you see there, that is the outboard dump valve for the pressurization system that maintains the pressure inside the aircraft and regulates and throttles the amount of air coming out. Obviously, it comes in from bleed air from the engines, but that is actually what controls the pressure in the aircraft. The APU, that's the inlet that you see there just below the N5 that feeds into that. This was the first aircraft that had this APU in this location, and that's pretty much become the standard across the industry, putting it in the tail like this. Okay, so look at the underside of the APU, and that's cooling air vent that you see. Going to give you a look at the actual exhaust from the turbine. And the role of the APU is to provide power, electrical power from a generator, and also pneumatic or air to provide for starting the engines or to augment cabin pressurization. So this is what it would look like if you were to remove the fairing. The single-piece rudder is attached to the vertical stabilizer. It has redundant hydraulic power supplies, but it also has limits applied as the aircraft gets higher in altitude and in speed. On takeoff and until an indication of 1,000 feet on a radar altimeter, it has 3,000 psi available. After that, it is reduced to 1,800 psi by the RPR. It has that until the radar altimeter gets to a reading of 700 feet on landing. This will give full authority at the critical phases of takeoff and landing. The rudder is also limited in its deflection based on airspeed. The pitot tube you see there provides that input, eventually getting down to just 4 degrees of deflection at 340 knots. Now we'll take a look at the horizontal stabilizer. The entire surface that you see there moves. You have the reference marks, the black marks there that represent the upper, middle, and lower travel of it. And that is adjusted by this jack screw that you see that moves the entire surface to trim the aircraft. So I thought that was a pretty neat video to include. So we'll just continue on taking a look around the aft end of the aircraft here. Now we'll start walking up the port side around the port wing and take a look at the engines. Now we'll take a look at the GT8D low bypass turbofan engine. It is a coaxial or two-spool engine. The high-pressure spool off the high-pressure turbine turns the high-pressure compressor, and the low-pressure spool turns the low-pressure compressor and the fan. You have a single-stage fan on the front, a 6-stage low-pressure compressor, a 7-stage high-pressure compressor, then 9 can-annular combustors, followed by a single-stage high-pressure and a 3-stage low-pressure turbine. And now we're going to walk around the aft end of the engine. The prototype, when it first flew, had the engine was shorter than this. Because of issues with the thrust reversers on the shorter engine, they added a 48-inch extension to the nozzle to make the thrust reversers more effective. Those you'll see them deploy here in just a second. But they allow for reverse thrust to shorten stopping distance. And here we go. You'll see as it deploys, it is a clamshell style. Now we'll continue around the front of the wing and the engine as we make our way forward. And you can see the Kruger flaps there that with hydraulics down, they have a tendency to droop because they're held up by hydraulic pressure. And you have the inlet to the port side heat exchanger there. And just a nice overall look at the aircraft down the port side. And now we're back to the nose of the aircraft where we started off just a few minutes ago. Now we'll take a look at the condition of the aircraft as it is now. It was a test aircraft for NASA that had a fully second cockpit installed here that you'll see in this NASA video that allowed them to change configurations, look at new flight instruments, flight control systems, as well as different weather and indications and testing for sensors. And it just shows the test crews coming in to man the aircraft. So now let's take a look at the outside of this beautiful aircraft. Thanks for sticking around all the way to the end. I really do appreciate you watching my content, and I do appreciate all of the feedback that I get, and I do appreciate it if you like and subscribe to the channel. And also I'd like to thank the Museum of Flight in Seattle. That wouldn't be possible without them maintaining these beautiful aircraft for us to enjoy.